All right, let's talk about what we had to do here. So first of all, we need to write the what? Yeah, let's write the formula. And the formula for nickel 2 hydroxide would be, and then what are we going to do? Okay, and that's going to leave me what? Oh yeah, just so we remember this, right? And so Ni's charge is going to be, nickel's going to be what? Plus 2, right? And that's going to be minus 1. And yes, there's a difference between plus 2 and 2 plus, but I don't care. And AP doesn't either. So that takes care of that. So now how might we write this? So KSP, okay? So I know 0.14 grams. What do I need it in terms of? I need it in terms of moles. And so in order to go from grams to moles, I need to do what? I need that good friend molar mass. So 0.14 grams. Right? And the molar mass of nickel 2 hydroxide is? 92.703. And 1 mole. So that means I have how many moles? 0.00151. Right? Y'all okay with that? Everybody good with that so far, right? So if that many moles dissolves, that's in the back. Let's see if this works. All right. So if I have that many moles of this, do I care about this? Okay. How many moles of this am I going to have? And how many moles of this am I going to have? So I can rewrite this, right? I could say, how would I write the brackets?
Bracket Ni plus 2, close bracket, open bracket, OH minus, close bracket, squared.
Y'all okay with that? That's going to be my KSP. Cool. All right, now let's do that. And then, so now I'm just going to take these numbers, this number, and plug it in here, right? And this number, do I put this number in here?
No.
What do I put in there?
You have to do 2 coefficient.
I got to multiply this by 2 first, right? So in this case, I'm going to have 0.00151. Okay, and after that, I grab my little handy-dandy calculator. We do some punchy-punchy. What do we end up with?
1.38 times 10 to the negative 8.
Well, that's not useful. Yeah, rounding's a good thing. Using this little crazy little rule we have in chemistry called what? Sig figs. This has 2 sig figs. This should have 2 sig figs. 1.4. So 1.38. Somebody said 1.35. Somebody else got? Okay. Cool. Y'all okay with that?
You know, I got it for the first time.
All right. Jess has got it, so that means we're good. Everybody's got it.
If I can do it, you
That's right. How's that positivity going? So if I give you the solubility of something, in other words, I tell you how much of something dissolved, you can tell me the KSP. And based on that, you can figure out how much would dissolve.
Would? No.
Like if I said, well, if I put this much in here and it dissolves,
Oh.
if I put this much in, what would happen? Right?
So we multiplied by 2 because that was the coefficient, right?
That's the coefficient, right?
Okay. Then we also squared by the coefficient.
Yeah. Remember, you multiply by 2 and square it. Okay, it has gotten colder. It's now no longer 20. It is down to 19. 19 degrees. It's a little chilly.
6 degrees below room temperature.
292 2 Kelvin.
Yeah, that's what I should write. I really would like someone. I'm really been looking for a Kelvin thermometer. I want a Kelvin thermometer for the back of my classroom.
So weird.
Yes, of course. I tolerate you.
It's a chemistry teacher.
Yeah.
When's your
Okay.
birthday?
So,
Summer.
yeah,
Is it in June?
no. The KSP value for copper 2 iodate is 1.4, yeah, you should have this one, right? Times 10 to the minus 7 at 25 degrees Celsius. Guess what? I gave you the KSP. Now I want you to tell me its solubility. How, based on the KSP, tell me how much I might expect to dissolve. Good? Got the answer?
Nope.
Working on it.
Okay.
I got a little bit, and then I'm stuck.
You got that far, right? Okay, we got that broken down. Okay, let's write the equation. How do we write this equation?
KSP
Uh-huh.
equals open bracket CU plus 2 close bracket open bracket IO 3 negative 1 close bracket square.
Y'all good?
Uh-huh.
Everybody's okay with that, yes? Okay.
And
Good?
then
So,
plugged in the 1.4 times 6 to the next 7 in KSP, and that's all I got.
well, what could I do algebraically?
I was gonna say, I just started algebra.
So mu is x, right?
Hmm?
X times 2x squared. When you multiply those out, you get 4x. Then you just solve x.
Yep. I think we all got to here, right? Okay. I know, the solution's a little. You should really fix the animations of these things. Divide by 4, take the cube root. And does everybody know how to do cubed roots on your calculator? Okay.
Just power to the 1/3.
Yes. Power to the 1/3.
Or the math in there. That's too much work.
Yeah. Just remember that's
Alpha y equals the right 6.
it's a lot of extra buttons.
Yeah.
You good? All right. So the solubility. So this is how much of this copper 2 iodate I should expect will dissolve at 25 degrees. It's always at a given temperature. Because remember, temperature affects the equilibrium. Good? We good? Good? You good? You all ready? Okay. I think y'all have these. Y'all have these? Well, if you don't, go ahead and grab yourself a fun little piece of paper and solve these.
Is your microphone on?
Always. You gonna say some rude stuff for me to document?
No.
When you're done with this, the unit is mole. Wait, actually, I already know the answer to that.
Alrighty, we'll take a few minutes here.
I got 1.606.
All right, let's see what we got here. How about this one? This one's going to break up into what?
AG 1 plus PO4 3 minus.
Oh, no, I did not.
Oh, then that explains it.
Oh, come on.
Yeah?
Oh, wait, no, I did that. No, I did
Okay. So my KSP is this.
Uh-huh.
So I'm gonna set this equal to what? 3x cubed
What?
x.
Yes.
Okay.
You multiply and go to the power of
What
this.
the heck? I wrote 27. Please.
Everybody okay with that fun? And then I'm going to divide by 3. Yeah? Good deal. And then I'll take the 4th root, right? Take the 4th root. And so x is going to equal what?
2.8 times 10 to the negative 5.
Okay, takes care of that one. Now that's x. But I didn't ask you for x, I asked you for solubility of this, which happens to be the same. So let's see if we got that right.
Oh. Okay, I guess.
Apparently not.
Wait,
Oh.
why is it divided by 3? Because it's 3x. But I thought if it was 3x. No. I thought, isn't it not 27x cubed?
Yeah, it is, because the 3 times 3 is 27x cubed.
So I was right.
It happens every once in a while. All right, so
You had it right too.
We're so good, Justin.
Dude,
so
what did I say?
right, so
So it is.
I was like,
So it
well,
is
the last one.
1.606.
yes, it's 1.6 is what you should end up with.
I want my Smartie. Thank you very much.
Who pointed it out though?
my chemist abilities.
Sorry. Overshot one, undershot the other. Let's do Smarties all around.
I won't smoke him this time, I promise.
Mila, you are what you eat. Here, throw one to Zach too.
Good catch, Zach.
Definitely. Sisters always need some of this. All right, after we do our punchy, we get what?
1.6.
times 10 negative 5.
That.
Woo, y'all awesome.
Yeah, apparently.
I don't care what your mamas tell me. All right.
My mom calls me awesome all the time.
Yeah.
My mom's like, awesome, you did something wrong.
It's a little more sarcastic in that case. All right, how about this one? This one's probably a little more straightforward, right?
Yeah.
Because this is 1 and 1, right?
Yeah, that makes sense.
And so this makes this going to be 1 and 1. So I'm just going to take the what? Square root.
Okay. Yeah.
We get what?
9.3 times 10 to the negative 5.
Woo! Y'all awesome. Good deal, good deal. Y'all see how easy solubility is?
You know what I think it is? It's because McKenna's not here. McKenna, I love McKenna. I don't want you
Well, since this is going on the TikTok channel now. Just TikTok, yeah. My TikTok stories.
No, it's like turning things my chemistry teacher who said into inspirational quote. I'll be doing that.
Have a day on the box. Have a day.
Yeah.
All right, here we go though.
So,
Let's follow some rules here. So you got to be careful about using this to predict relative solubilities. Okay, you can't simply compare these to determine relative solubilities. You got to be careful when they're producing a bunch of different ions,
Oh, yeah.
because your numbers, like this number's going to look crazy, and you go, well, it has 5 ions, right? That was another one that y'all missed a lot. Like how many ions things have, like which one's going to be the most which one's going to produce the most number of ions, and a lot of y'all wrote down 0.4 moles of sucrose. 0.4 moles of sucrose will produce exactly how many ions?
0.40.
Because sucrose is what kind of a compound? It's covalent. It's not an ionic compound. Therefore, it's not going to make any ions.
I don't remember that.
So a lot of people put that. That's another one. There's that's another question. There's like 3 or 4 different versions of that question.
Still open.
Okay. All right. So let's look at now what's called the common ion effect. So the idea here is the solubility of a solid becomes low when the solution already contains ions common to the solid. I want you to think about this from a equilibrium perspective. All right, so I'm going to use a really simple example, because I don't think this one does. Yeah, there's no real example. So here, let me give you a silly, simple example. I've got NaCl. That breaks into Na plus Cl minus, right? Now, what if instead of NaCl, I already had a solution that had a bunch of chlorine in it? So perhaps I had a solution of KCl. Okay? I already have this, and it's already saturated, which means I've already got a bunch of chloride ions. This has the same effect of increasing the chloride ions. And if I increase one of the products, which way is it going to shift? It's going to shift the whole thing back this way. So because I already have a bunch of this, I'm not going to be able to dissolve this, or as much of this as possible. y'all follow me? So I'm going to say I've got a solution of potassium chloride. Already dissolved. We know it completely dissolves. Potassium chloride completely dissolves. I'm going to take something like this. Actually, it'd be better to use something that doesn't dissolve completely, but we're just pretending. So I've got chloride ions that are already saturated. This solution is holding as much chloride as it possibly can. If I throw sodium chloride into it, this is not going to actually dissolve because it's already saturated. This has the effect, the same effect as if I had increased the concentration of chloride, driving the reaction back to the left. That's all the common ion is. That's what the entirety of the common ion effect is. Figure out something that already exists in the solution or could exist in the solution and what's going to happen. So that's version 1. Version 2 is the other thing that's going to happen here is because I've just added a bunch of chloride, this reaction is also going to go back this way. Yeah? All right. So that's conceptually what's going on. And we'll go with the bigger words here now. All right. What if all I know about two salts is that the value of KSP for salt A is greater than that of salt B? Okay? We're not going to worry about that. We are going to talk about how to do this common. I don't know why that one should have happened before the common ion slide, but I'll go back here. This is our common ion effect. Here we go. I've got solid calcium fluoride. Good, page 4 for those two of you who are still at home. So there's KSP, yeah. In a 0.025 molar sodium fluoride solution. So I already have, now sodium fluoride is going to be totally soluble, right? Because it's sodium. By the solubility rules, if it's got sodium, it's going to be totally, that means I have 0.025 moles of, and 0.025 moles of the fluoride, right? If I have a solution of sodium fluoride, it completely is dissociated. So that means if I started out with 0.025 molar sodium fluoride, I'm going to have 0.025 molar sodium and 0.205 molar fluoride. Y'all follow me? Now I'm going to put calcium fluoride in there. And what I want to know is how much of that will dissolve. What's the solubility of that given the KSP? Ready? Let's take a look conceptually. I want you to think about what's in there right now. What's in there right now, and I'm going to write it here just because it's kind of weird. I've got sodium. I've got fluoride. I've got water. Those are that's what's in the solution right now. Major species. Because we know anytime I've got water, I've got some hydroxide and some protons and whatever. They're really small. But these are my major guys. Okay? The solubility equilibrium. Can you write the rule for that? What's the rule for that? Go ahead and write that. What's the rule for this? How do I write that? That's my balanced equation, yes. You've got to write that first. You'll have to do that whenever you do your work.
Got it. Just kidding. I know.
See what we got there now? So now,
Oh.
right? Are you happy now?
What is the?
Because this is what we started with.
Oh.
That's what we started. We started out with 0.025.
Right.
We've added x and 2x because I can't get any more of this unless I also get that. But the amount of this is going to push the reaction back that way. Now we just need to find out how much.
Oh. Hmm.
Y'all okay? If you need to, go ahead and do the punchy punchy and see where we're at. Huh.
Oh no, I think I see the project now.
Remember, we get to do these little things? KSP is really, really, really small, so we're going to pretend like it doesn't exist.
What? What? You can't do that.
Yeah, we can. It's chemistry, gray math. We could do it. You could actually type the thing. So somebody who has this, type it in and get to the solver and see. Type it into your get. Type this equation into the solver and see what you get. If y'all have not figured out how to use solver, you've got to do that. Yeah, it's only for, regular people. Regular people. Because you can solve this with just a little baby calculator, right?
Yeah.
This is really, really small. This is really, really large compared to that number. That's really, really large. So the x is not going to be that big. And in fact, whenever we solve this, it turns out that x really isn't that big. And so it was reasonable to simply ignore it.
That's dumb.
Well, put it in your solver and see how close it is.
No.
Wait, is there a 5% rule in the AP test?
Yes, of course. Yeah, you will. If you find yourself staring at something that you think needs a quadratic, you're wrong. Okay. Like, you will never use it. You just need a statement in there that says, since KSP is small, or KC, or whatever it is you're estimating, because this is whatever it is super small, we're going to ignore it and use the 5%, or use the we're going to ignore it, okay, and have the approximate answer. And as long as you state that, like literally say that, you're going to be in good shape. This says that if I have a solution that's 0.025 molar already, I'm going to be able to dissolve 6.4 times 10 to the minus 8 moles of calcium fluoride. Now, if I wanted to, I could compare that to how much I could do it in pure water, how much I could dissolve in pure water. Yeah?
Can you neglect like that thing for every question?
So that's what I was saying. So for your homework, no. For my test, probably not.
Then why are we
But for the AP test, definitely. No, I hope on my test you'll. Basically, as I said, when you get to the free response, if you, yeah, if it, huh? Yes. Yeah, probably.
Are we gonna have this for homework too?
Yeah. Oh yeah.
Now that I have a really good understanding of what's happening, I'll do good on the free response.
There you go.
Are we gonna have a free response?
Yes. Yeah, we'll start free response. Maybe next week.
what?
Okay. So this X, and therefore, since that's a 1-to-1, good?
Can't make it back.
Enjoy. Yeah, we're stopping there. Good? Yeah, you know, time flies when you're having fun. There you go.